So what I'm telling you that this is D0 bit, D1, D2, D3. So this D3 bit position, that is the position of higher nibble, that is the position of higher nibble, higher bit of one nibble, and D4 bit position, that is the position of LSB bit of second nibble. Okay, so from one higher nibble, higher bit of one nibble, if the carry is pass on to the next bit or next nibble, okay, lower bit of next nibble, only in that condition the auxiliary carry flag will be set. Otherwise you don't need to consider anything else. If any carry is generated into D3 bit, any carry it results from bit D3 and passes on to the D4 bit or next bit, then only, that means from the lower nibble to the higher nibble, then auxiliary carry flag will be set. And also this carry is also called the half carry. Okay, it may also occur in the process of a subtraction operation, and in other words, at that time this flag is set if the subtraction operation results in borrow. Okay, so these are the different flags operation, these are the different flag condition when they are changed. Okay, so next is the program counter. Program counter, okay, it is so important, it is so special, because without this program counter register, no operation will be started, because everything will be started from this position. Okay, from this position, so the processor working principle will be started from this position. So program counter, that is a 16-bit register that always points to the address of the next instruction to be executed. Okay, so we have to write an instruction, so that instruction should be stored in some memory location. So without identifying the memory location, nothing will be processed. So first microprocessor needs an address, and that address should be given by this program counter register. And as memory address is 16 bits in size, so that's why this register size is also 16-bit. Program counter, that's why the program counter register size is 16-bit. Okay, in other words, it is called this register, it is used to sequence the execution of the instructions. So after execution of every instruction, the content of the memory location indicated by this program counter, that is moved to the instruction register, and the program counter is loaded with the next address. Suppose I have started my program from 8000 memory location, 8000, 8000 memory location, and it is going up to 8009 memory location. So first instruction will be fetched from 8000 memory location, then the next instruction from 8001, then 8002, then 8003. So in this way, sequentially, one by one, instruction will be fetched from the corresponding memory location. So who gives you the memory location? Microprocessor needs to know the particular memory location from where the next instruction must be fetched, and that instruction address, that memory address should be provided by this program counter register. So always this program counter register will be incremented by 1 when the corresponding instruction must be fetched by the corresponding memory location. So after each memory location, the memory location will be incremented by 1 automatically, and it will be provided by the program counter register. Okay, so it holds the address, that's why the register size is 16-bit. So program counter size is 16-bit. Why it is so? Because always it needs to store the address. Whose address? The address of the next instruction that is to be executed. Okay, and that increment or decrement of memory address okay, will be performed by this incrementer or decrementer latch, which is given here over here. Okay, incrementer or decrementer address latch. So every time this address should be incremented by one by the help of this circuitry, and it gives the address through this address bus. Okay, it gives the address through this the address must be transferred through this address bus. So it gives basically it keeps track of a program by counting the memory address from which the next byte is to be fetched, and hence the name as program counter. Clear? Next is the stack pointer. Next special purpose register is stack pointer. So stack, that is an array of memory locations in RAM. Array of memory locations. It's a group of memory locations in RAM only. That is not ROM. Okay, don't confuse, don't uh, mistake this one. So what is stack? Stack is a group of memory locations in RAM. Okay, which executes last in first out structure or first in last out structure. Okay, so and it is accessed using a 16-bit pointer register called stack pointer. So in the same way, just like a program counter, it holds the next instruction address. So stack pointer basically it holds the address of the memory location of the top of the stack. So few memory locations are used for stack operation, where some structured data will be stored, and that structured data should be one by one will be processed according to the requirement, according to the requirement by the user or by the programmer. Okay, and this stack memory locations will be initialized at the last portion of your memory, because uh, the RAM which is used, that is used for writing a program, that is used for that is used to store some random data, and that is also used for uh, or to store the structured data. Okay, so random data that can be used any memory location, and structured data should be followed in this way: last in first out structure or first in last out structure, and this is called the stack. So this stack memory location should be initialized by some register, and that register always holds the address of the memory location from where the stack is initialized, from the stack from where the stack is um, started. Okay, so that's why the size of the register is also a 16-bit, because it holds the memory address of the stack, top of the stack. That's why the stack pointer register is also a 16-bit register. Okay, and the programmer can reserve and
Excuse me, sir.
yes.
Sir,
Yes.
kindly explain this stack pointer again, sir. So it's a little bit confusing.
Okay. Uh, Wait a minute. Can you see this paint?
Yes, sir.
Okay. Suppose this is my memory locations. Okay. Total 64 kilobytes of memory is there. 64 kilobytes of memory, the total size. So this 64 kilobytes of memory can be used for different purposes, like to store your instructions, to store your data, input data, again to store your output data also. So memory locations are just like, look like this. It just look like a notebook. Several lines are there. So these lines basically the space where some data can be stored. Clear? So 65,536 this type of locations or space is there. Now what is the starting memory address? My starting memory address will be always 0000. in hexadecimal number system. Okay, 16-bit memory address. Memory address is 16-bit. But how much data will be allocated for this space? Only 8-bit. Only 8-bit, like 30. Like I have written 30. Okay, 30 is a it is an 8-bit number in hexadecimal number system. Okay, 30 can be written in this way: 0011 0 0 0 0. Understand? In binary form, it is written in this way: 0011 0000. Okay, 30 can be written in this way. 30, that is in hexadecimal. If you convert it into binary form, that can be written in this way: 0011 0000. So it will be stored here in this position, but the address is always 16-bit. Okay, so one by one these addresses are 0000. Then next address will be 0001 0002 0003 0004, and all the way up to last location will be FFFF. Clear? Last location will be FFFF. And among these memory locations, how many memory locations are there? 65,000 memory locations are there. Okay, so generally what happened in practical purposes, the initial memory locations are used for programming purpose. Okay, used for programming purpose, used to store some random data, means input data will be there, some output data will be there in this way. Okay, and the last portion of your memory space, that can be used to store some structured data, or it is used for stack operation. It is used for stack operation, stack, stack operation. Okay, so in your like in real world example is your messages. Okay, whatever be your messages, which is a normal message or WhatsApp message, everything will be started from the last in first out structure. The last message will be shown you first. Okay, so this portion of memory will be used for stack operation, so that stack is implemented in your phone. Okay, in real life this stack operation is used in this way. So the last portion of your memory space will be used as stack, and first portion of your memory portion will be used for programming purpose. Okay, or to store some data purpose. So if you use them in this way, so there will be no chance to overridden of this thing of your programming data or the instructions or the data bytes with this stack data. Okay, so that's why we need to create the program in this way, and we need to create the stack from the last portion in this way. Clear? So programming যখন আমি করব, it will be going in this way. বাট যখন আমি স্ট্যাকের মধ্যে কোনো ডেটা রাখবো, তখন এই রকম ভাবে রাখবো, লাস্ট থেকে ফার্স্টে। আর যখন স্ট্যাক থেকে কোনো ডেটা we need to retrieve it from the stack memory location, the last data will be processed first. Okay, last data will be processed first, then the next one, then the next one. So last in first out structure. Clear? So programming যখন আমি লিখছি তখন এইভাবে যাচ্ছি ফার্স্ট থেকে লাস্ট, আর যখন স্ট্যাক অপারেশন ইনিশিয়ালাইজ করছি বা স্ট্যাক নিয়ে যখন কাজ করছি, তখন ইট উইল বি প্রসেসড ইন ফ্রম দ্য লাস্ট পজিশন টু দিস ওয়ান। ক্লিয়ার? দুটো অপোজিট সাইড থেকে শুরু হয়, যাতে দুটো ওভারল্যাপ না করে। হ্যাঁ, ওভারল্যাপ করলে কি হবে, একটা ইনফরমেশন আরেকটার উপরে মানে হয়ে গিয়ে আমার ডেটা লস হয়ে যেতে পারে। ওকে, সেই জন্য অলওয়েজ ট্রাই টু ইনিশিয়ালাইজ ইউর স্ট্যাক মেমোরি লোকেশন at the last portion of your memory space. Is it clear?
Yes, sir.
Yes, sir.
Any doubt, any confusion?
No, sir. This one is clear.
Okay, so this will be more clear when we'd like to perform certain programs, okay, later. So right now just you need to clear the concept what is the stack and how it will be initialized, or what is the stack pointer function also. Program counter, stack pointer function. We just need to clear this concept. Okay, so move on to the next slide. Hmm. Is it visible, this slide?
Yes, sir.
Okay,
Yes, sir, visible.
so one thing, so while the programmer actually uses this is very important, you must remember. So when the programmer uses the stack for storage and retrieval of data, uh, the microprocessor uses the stack during subroutine calls, okay, when it calls another program from main program. So care must be taken by the programmer, okay, to ensure that the data stored in the stack is retrieved properly, so that the data stored in the stack by the processor is not affected in any way. Okay, the next special purpose register is the instruction register and instruction decoder unit. So it is an 8-bit register that usually temporarily stores the instructions drawn from the memory location. Okay, so memory location থেকে যখন instruction, it will be fetched, microprocessor fetch the instructions one by one from the memory. So somewhere it must be stored, কোথাও না কোথাও তো একটা জায়গায় রাখতে হবে, হাওয়াতে তো ঘুরে বেড়াতে পারবে না। Okay, so it needs something where it should be stored, and that space is here. So when a microprocessor fetches the instructions one by one, it will be stored here in this instruction register. And from this instruction register, so before the actual execution, the instructions are temporarily stored over here, and the content of register is decoded by the decoder circuitry, where the nature of the operation is to be performed, that is to be decided, that is interpreted. Okay, which type of operation is to be performed. Then in addition, there are two temporary registers are over here. It is not mentioned here. W and Z will be here. Okay, the upper portion of your B and C, this will be another two registers, but these are temporary registers. Those are available, those are not available to the programmer or user. Okay, this W and Z, these two temporary registers, which are controlled internally and internally by the microprocessor and not available for user access. Okay, so these two registers are used to store certain type of data. Okay, so instructions are first stored inside the instruction register, then data will be stored inside some temporary register W and Z, and from where the next operation will be carried out. Okay. Next is the timing and control unit. Uh, the timing and control unit, actually it gets commands from the instruction decoder, and issues signals on the data bus, on the address bus and control bus. So that means the system bus must be controlled by the with the help of some control signals. Okay, state timing and control signals. And just like our our brain gives the signals to everywhere. Our hands, legs are performing in such way when the signals are coming from our brain. Suppose if I want to take a pen on my right hand and it is shifted to my left hand, so who performs this thing? Our hands. But who gives the signal? Our brain. So here the same thing, these registers, these different registers are over here, or the buses are over here, by which the operation is performed. But who gives this signal? The brain. And where is your the microprocessor brain? That is the timing and control unit, from where the different control and signal status signals or the timing signals will be given, and as per the signal is given to the different hands and legs of this microprocessor, they are performed according to that signal. Okay, just like one example, suppose I have written one instruction that is to load, if I want to add a number, two numbers, 8-bit addition, suppose 02 plus 03, the same example. So mvi a comma 02, if I have written in this way, suppose I have written mvi a comma 02. This is one instruction, 02. Second instruction is given as mvi b comma 03. So these are instructions. Okay, means 02 must be loaded inside accumulator, 03 must be loaded inside b register. So তাহলে a এর মধ্যে কি আছে 02 আছে, b এর মধ্যে কি আছে 03. Okay, so these two numbers are loaded inside two different register. Now what I need to do, I need to perform the actual operation. What is the operation? Addition. Suppose addition. So addition instruction can be written in this way: add b, add add b. I've written one small example. Add B means addition between the content of accumulator to the content of B register, and by default when this addition is performed, finished, the result will be stored inside accumulator. Clear? So now according to this instruction, the meaning is this one. Add B means addition of accumulator content. Now what is the accumulator content? 02 with the addition of content of B register. What is the content of B register? 03. Now 02 plus 03. What will be the result? 05. Now where it will be stored? This will be stored in accumulator. Clear? So when this instruction is fetched by the microprocessor, it must be stored in instruction register. The first instruction stored in instruction register, then 02 must be stored inside accumulator according to this instruction. So 02 চলে গেল accumulator. Okay, so 02 চলে গেল accumulator. Now কোনখান থেকে যাবে? ফার্স্ট কে কি কাজ করবে? mvi a, 02 আমি যে লিখেছিলাম, so that is in some memory location it is stored. So program counter, from program counter the address must be given, and through that address, after getting this address, the corresponding data means corresponding instruction will be passed through this transferred through this bus, so that the first instruction will be fetched and it will be stored over here, and from here mvi a must be decoded, and the function of mvi a means move the content into accumulator. So it demands for the content. What is the data? 02. Now next 02 must be fetched using this bus, and 02 must be loaded inside this accumulator through this bus. Okay, so 02 এখানে load হয়ে গেল. Next instruction is mvi b, 03. So again mvi b, 03 will be loaded in this way. So in b register 03 will be loaded. Okay, then what will be the next instruction? Add b. So when add b is executed, so using this timing and control unit, the given signal is to be the required signal is to be given to this ALU circuit, that you need to add them. Then from this position where it is it stores the 02, then 02 moves in this way, and 02 will be taken out from this way, and it is stored inside the temporary register, and from temporary register it goes into ALU. Then it gives the signal add B. Then addition of accumulator and the B register content will be added over here, and when this one is finished, the 05 will be generated, and again it gives the signal to the accumulator. You have to capture that data which one is generated now. So according to this signal, the accumulator gets this data when it is generated over here and go through this line, and it is stored inside accumulator. So 05 will be loaded inside accumulator. So in this way every operation will be carried out. Okay, that is the basic structure of the operation. Is it clear? Everyone, do you have any doubt how it works? This is the easiest way to understand, because every arrow, it has some significance. And one significance over here, every block is a square or rectangular size block. only the ALU is this type of shape. Why? Because it it signifies that it needs two inputs and one output. Two inputs and one output. Okay, and from where the input will be coming? From the accumulator and from the temporary register. And when this one as these inputs has been given to this ALU circuit, after that, according to the command signal, according to the instruction, it will be operated and it generates a result. And again this result is going transferred through this bus, so that when it is over here, the accumulator can capture this data and loaded inside this. So that's why this arrow is always given in the down arrow sign. Okay, so all these are loaded. Now this is bidirectional arrow. Okay, bidirectional. Why? Because some data byte can be stored inside the general purpose register, or can be given from this register, so can be taken out from this register. Okay, so data can be stored or data can be retrieved in any time, according to the instruction, according to the command. That's why it is a double arrow. Okay, bidirectional arrow. So every arrow has some meaning. So don't confuse with this arrow. These are all downward arrow. So that's why that means every operation is coming through this way, not in this way. Okay, whatever be the microprocessor face the data or instructions, so everything will be processed in this way and it is stored in this way. Okay, in this way, not the upper or upward arrow. It is always these are downward arrow. Clear? Clear up to this much? Tell me, is there any
So
confusion?
one small doubt, sir.
Yes.
Sir, in case
Hmm.
I write that add B operation again,
Hmm.
add B or instruction again, will it
Hmm.
add the value of 3 to
Hmm.
5?
Yes, yes, because now accumulator accumulator stores the 5. So if you write down the same instruction add B, so content of B is fixed, it is not changed. Which one is being changed? The
Yes.
accumulator, because every time accumulator gets changed. So now the current value of accumulator will be added to the previous value of the same value of the B. So 5 will be added to the 3. Now the result is 8. So again 8 will be stored inside the accumulator.
Okay, sir.
Okay. Okay, anyone else? Okay, I have already explained these signals last day, the control signals, status signals. Huh? So I'm not doing this again. Interrupt has been, some of these interrupts has been discussed, like it has uh, microprocessor has 5 hardware interrupt pins: INTR, RST 5.5, 6.5, 7.5 trap. I have told you earlier, no? Can you remember this? Is it discussed last day? This interrupt, how many interrupts were there? Okay, again I am discussing this thing because it is very important. The interrupt, basically these signals are used to make the microprocessor respond to high priority externally initiated signals. Okay, so when an interrupt signal is detected by the processor, it suspends the execution, current execution, and executes the program corresponding to the interrupt signal in based on the interrupt processing signal. Okay, so the interrupt service routine will be processed. So 5 interrupt signals are there through which, or 5 hardware interrupt pins are available through which the 5 interrupt signals are coming. One is the INTR. Over here you can see it over here, INTR, RST 5.5, RST 6.5, RST 7.5, and trap. Okay, through these 5 pins, the five external signal can be coming. Okay, and these are available to facilitate the processor to receive and acknowledge the interrupt call of peripherals. Okay, so these are interrupt. Okay, another pin is available as interrupt acknowledge. So if any interrupt is coming through only INTR pin, only this pin, only through this pin, if any signal is coming at that time only, from microprocessor, it gives an acknowledgement signal to that device which interrupts it. Okay, and that is called the interrupt acknowledgement signal. Okay, interrupt acknowledge signal. So this signal, this, so if any signal is coming through this INTR pin only, at that time interrupt acknowledge has been sent by the microprocessor to that corresponding peripheral device. Okay, another another is uh, here one block is over here, serial IO controlled. This one has been already told you earlier, last day. So basically this is used for serial input output operation purpose. Okay, serial input output control purpose. So if any one if any signal is to be uh, received, is to be given by the, actually this one, this two arrow, these are wrongly printed. Actually this will be in downward, this will be in upward position, because it is used as output data. So using this pin, the serially the data will be transmitted serially, and through this pin data will be received serially. Okay, so these arrows will be opposite inside. Okay, this will be downward and this will be upward. Just correct it. This will be downward, this will be upward, because it is for serial input data, it always receives the data, and this is transmit the data. Okay, that's why it is always external. Hmm. So this is the architectural block diagram. Okay, so demultiplexing of address and data bus. How can you demultiplex the address and data bus using this? So this diagram helps you to understand this thing. Uh, so we know that we have 16 address lines. Okay, from A0 to A15, but among these 16 address lines, only 8 address lines are multiplexed. Okay, what does it mean? That means the same line, it is used for dual purpose. Dual purpose means for address transformation purpose, transfer purpose, and for data transfer purpose. Okay, but not at the same time. Okay, first address will be transferred, then when address is identified, the corresponding data will be transferred through uh, using the same line from the corresponding address. Okay, and who helps this works to perform? uh, ALE. Actually, this ALE, address latch enable signal, it is used to latch the data, so that first uh, address will be transferred, and when this latch circuit is disabled, data will be transferred. And this one is over here, the latch circuit is enabled. Now if latch is enabled, only address will be transferred. Okay, when latch is disabled, only data will be transferred. Okay, so how can you demultiplex the address and data bus? So here is the diagram. Can you see it properly?
Yes, sir. So, but the writings are not that much clear.
This is the higher order address bus. This A0, sorry, A15, A14, A13, A12, A11, A10, A9, A8. Okay, these are called higher order address bus. and this is the latch circuit. This is ALE signal which is enable, and this is AD0 to AD7, AD0 to AD7. So initially AD0 to AD7, when this latch is enabled, after this latch only lower order address bus will be generated, lower order address will be generated from A0, A1, A2, A3, A4, A5, uh, A5, A6, A7. Okay, but when latch is disabled, no address will be transferred, only data will be transferred, so that the data buses are over here from D0, D1, D2, D3, D4, D5, D6, D7. And that is the demultiplexing of address and data bus. It's a very important question for your theory as well as for theoretical purpose. Okay, theory in semester exam. Okay, how can you demultiplex the address and data bus? You have to draw this diagram and explain these things. So what I am just trying to say you that you have to mm, address, you have to enable the latch circuit so that address will be transferred, and if this is disabled, the data will be transferred. Okay, because initially it is multiplex, and we just needed to demultiplex again for address and data operation, transfer operation. Okay,
Okay, sir.
and that is the overall picture. So putting all of these thing, those concepts which I have told you, uh, we get this thing. Here is your processor, microprocessor. This is the memory which is external to the processor. Hmm, and how this memory is connected with this microprocessor using these control signals. Okay, when it's to enable this memory IC, enable this memory portion, you need these control signals. Either anything can be read from the memory or anything can be written into the memory, and to access this memory you need this address bus. And how can you transfer the address? It will be transferred from this one. And who gives you the address? The program counter will be given this address. Okay, so after getting this address, the corresponding data will be fetched from this using this data bus, and it will be given to the processor. And if anything is given to the memory, then processor will give this data through this data bus, so that it will be written into the memory. Okay, so this is the overall configuration with the help of microprocessor as well as the memory and different control signals and the system bus. Clear? Clear up to this much?
So just a small verification, sir.
Hmm. Okay.
So that means
Hmm.
this interrupt calls signals or the interrupt call pins
Hmm.
are for receiving the interrupt calls from the peripheral devices.
Yes, yes.
That is to give priority to that device and
Hmm.
stop all the works that are being presently performed by the microprocessor.
Yes, yes, yes.
And so in case the signal
Hmm.
is obtained through the INTR pin,
Hmm.
then an acknowledgement signal
Given to that particular
would be
device.
given. Oh,
Okay.
okay, sir.
Hmm. Because interrupt means some external signal. Okay, interrupt will be always some external signal. Okay, interrupts can be generated inside the processor also, but that is the software interrupt. Huh. But harder interrupt means some external signal is given from the outside world to the processor. Clear?
And so